Now let's turn to exploring the dynamics of the logistic model. So you might remember that n of sub t plus 1 is the population at time t plus 1, and that was equal to the birth rate minus the death rate times the population at time t minus the number of individuals who die due to overcrowding, which is the population at time t squared divided by the maximum population, or the carrying capacity. I'm going to start by writing this in a simpler format. First, I'm going to let R represent the birth rate minus the death rate, and I'm going to let K equal the maximum population. Now I can write this top equation using these new symbols. Now I'm going to do a little bit of algebra. So if you don't like algebra, then just try and follow along, and if you don't understand it, it doesn't really matter. It's only the endpoint that you need to know. So what I'm going to do is divide both sides of this equation by K, the carrying capacity. And now I'm going to define one more new symbol, and that's going to be x sub t is equal to n sub t over k. So now I can rewrite this equation using my new symbol x. This equation represents the fraction the current population is of the carrying capacity at a given time, and that's equal to R times the fraction at the previous time step minus that same fraction squared. And this is known as the logistic map. And this turns out to be the most famous equation in the field of chaos theory. Let's rewrite the logistic map here for clarity. Really simple, huh? As it happens, though, it's more interesting than it appears. Many people have studied this equation in depth since Verhulst proposed it. Two prominent examples of people who have studied it are Lord Robert May, a theoretical biologist who wrote a very influential paper about this equation in the 1970s, and Mitchell Feigenbaum, a theoretical physicist who worked extensively on this equation in the 1980s, and is probably the person most commonly associated with it in the scientific community. Note that x is the population at some time divided by the carrying capacity, or the maximum population. So x always is a real number between 0 and 1. This is why the equation is called a map. That is, it takes on this side a current value of x between 0 and 1 and maps it into a new value of x which is also between 0 and 1. So let's look at an example. Let's let R equal 2 and our initial population over carrying capacity x0 equal 0.2. That is, our population is 20% of the carrying capacity. Now we can iterate this map, so get out your calculator. Let's calculate x1. That's going to be equal to 2, that's our R value, times 0.2 minus 0.2 squared. And according to my calculator, that's equal to 0.32. So we've gone from 20% of our carrying capacity to 32%. Now what happens the next year? At the next year we have 2 times, well, now we got to take this value for our previous generation, 0.32 minus 0.32 squared. And that's equal to 0.4352. Okay, let's keep going, but a little faster now. And forever after, we'll get 0.5 as our answer. This means that if your growth rate, that is the birth rate minus the death rate, or R, is equal to 2, and you start out at 20% of the carrying capacity, under this model, the population will always end up at 50% of the carrying capacity. There are two things I should note here. First, I'm using the term model here to refer to a mathematical equation, that is, the logistic map. This is the model. It's called a model because it's a simplified representation of the real phenomenon of population growth. I'll also refer to the computer programs we write or use in NetLogo as models, since they're also simplified representations of real phenomena. The word model is a very general term in science for any simplified representation of nature, whether it be an equation, a computer program, a drawing, or what have you. The second thing to note is that this value of 0.5 is called an attractor. It's an attractor for the system because the system is, in some sense, attracted to it. It turns out that even if we had started with a different initial population, say x0 equals 0.8, the system would still end up with a value 0.5 after some number of steps. When the system ends up at a single value, like 0.5, this value is called a fixed point. Since the value, or the point, stays fixed. Thus, for this system, 0.5 is called a fixed point attractor. And by this system, I mean, again, this equation with R equal to 2. Often the terms model and system are used synonymously. I hope this doesn't get too confusing. In any case, we'll see some other kinds of attractors in the next subunit. Finally, let's look at a different way of visualizing the dynamics of the logistic map. That is, how it changes as you iterate it. I'm going to draw a plot of the logistic map equation for R equals 2. Now what I'm plotting down here is x sub t, and what I'm plotting over here is x sub t plus 1. Okay, so not a great drawing, but this is roughly what it looks like. It's a parabola, and it goes between 0 and 1 here, and here for r equals 2, I'll write that, it goes between 0 and 0.5 is the maximum. Okay, let's put 0.5 here on the x-axis, and then we can follow the steps we took before in calculating the values taken. Okay, so our first value, if you remember, x1 was 0.32. So that's x1. We find this on the 0.32. It's about right here. And the y value for that on the parabola was 0.4352. That was x2. Okay? So this was the point x1, x2. Okay? Then we take our value for x2 and we find it down here on the x-axis here, because we're going to calculate the next value of the function. So 0.4352 down here is around here, and that corresponds up to this point. On the parabola, that's x3, 0.49160,192. Okay, this point here is x2, x3. Okay, then we take our old x3, which was 0.49160,192. We find that on the x-axis. Then we go up here to find x4, which was 0.499999, etc. Okay, and we keep doing that. And finally, we get to exactly 0.5 and 0.5. And once these are both 0.5, the system doesn't go anywhere. It always just stays at this point. So you can think of hopping from one point to another along this parabola as an example of the dynamics of the system with this R value and our starting point, and that is called a trajectory. Now it's time for our next quiz. You'll need a calculator for this quiz. Set R equal 2.5 and x0 equal to 0.2. Then use the equation for the logistic map, filling in 2.5 for R and starting out with x0 of 0.2 to calculate x1, x2, x3, and so on until you've reached a fixed point. What is that fixed point? And recall that a fixed point is a value of x such that x sub t is the same as x sub t plus 1.